So then we get into some other system voltages, and it says, unless otherwise specified, under a special circumstance, nominal voltages of 120 volts, 120 240, 208Y, 240 volts, 347 volts, 480Y, 480 delta, 600 volts, standard voltages for standard electric services should be used. So, these are somewhat arbitrary in what you use. There may be small differences in terms of three-phase power versus split-phase power. The important part is to match. When you get into commercial design, it may be that if you're picking out what kind of transformer to use, that, let me bring up my laser pointer again, that you might, if you're choosing to hang a transformer on the power line, you might have a choice on, do you want to do 208 or 480Y, and typically you'll opt for 480Y simply because by having twice the voltage you have half the amperage, and so you get more bang for your buck in terms of conductor sizing at a higher voltage rate. In fact, the longer you transfer electricity, the higher in voltage you want things to go. So, you have to think about that too when you're doing a ground mount design. Is it better for me to be at high voltage and then go underground with that high voltage to the inverter on the side of the building, or is it better for me to put the inverter out of the field and step down the voltage to 240 volts, but provide some stable voltage going back to the house? I think there's an argument to be made for residential ground mounts of hanging the inverter on the side of the building and doing a lengthy underground conduit run using DC wiring. And for that matter, maybe the Solar Edge optimizers on a ground mount that step the voltage up to the top of its voltage range have some application, or at least string level optimizers in ground mount services for that matter. So then we get to branch circuit feeders and service calculations, and this is a 120 240 split phase voltage is the typical U.S. residential service. And so what we have is an actual 240 volt service coming in from this transformer on the side of the power line. So this is what the transformer looks like. That transformer is hooked into a distribution circuit that is running at about 2,400 kilovolts. And it's running through a transformer, and this transformer has a neutral point. And that neutral point is 0 voltage with 120 positive and 120 negative alternating current. And from point to point, you have a total voltage potential of 240 volts. And then from point to neutral, you have a voltage potential of 120 volts. And so what that means is on a solar inverter, it's a 240 volt device. And it'll actually take up twice as much space on your service panel because it's going into both legs of power. In other words, you have a leg 1 and leg 2 of power on a residential service, and that goes all the way up to the box on the rooftop, whereas most of your power outlets are 120 volts, and they're just stacked on either side of the service in somewhat of a balanced process. So the transformer is taking our utility distribution voltage and stepping it down to stuff that our home can use. In fact, I found it difficult doing complete design work in solar because I didn't know what any of this stuff was. So it was, well, what am I responsible for providing to the utility? Am I bringing this cable out? Am I buying this, whatever this thing is? Well, here's your power lines, and here's your neutral. And what we note here is that we have a ground wire that's grounding this transformer to ground. And in the transformer itself, somewhere between the transformer and your utility meter, they're going to be connecting that neutral line to ground as a reference. And that reference voltage forms the basis for our entire grounding and bonding system. So, you know, what you're providing, usually the utility comes out and they will hang a new transformer if need be. Like if we're establishing a new electrical connection, they connect to the power lines, they transform that distributed voltage into whatever your electric service is. It's a transformer specific to your service. And then the way we do it out in Mississippi is we provide the meter base and the utility meter, although we have to check with our local jurisdiction to see which meter and which meter base they use. Sometimes they're picky about that. So we try and be a standard to what the local standard is. And then this is called a masthead and a gooseneck. And what this is for overhead cables. You know, sometimes you might look at these overhead cables and you think, wow, why are these wires just kind of hanging out here? And sometimes they're taped off, but they have to hang out because right here it's called a drip loop. So when it rains, water comes down the line, and that water could go straight into the metal and then drip down in the meter and short it out. So electricians install a drip loop to keep the water out of the weatherhead. Now, that problem exists in the solar industry too. You have cables going into an electrical box on the rooftop, and you know, when I came into the industry, I didn't know that I had to put a little drip loop on the cables going into the box. You know, that's something they teach in electrical training. I didn't get that level of install training in any of my solar classes. I like using electricians to do solar installs because they have good, basic electrical hand skills. And if you want to get into solar installation, it just makes sense to pursue electrical apprentice journeyman route. It'd be more valuable anyway. So here we have a utility service entrance conductors on a drip loop going into the top of the meter base, and then the power to the property comes out the bottom of the meter base. And you have to take note of all of this stuff, how the power enters the property. It can come from above ground. It can also come from underground power lines, at which point you might need the opposite. You might need a bottom fed meter and then come out the top before going to your electric service. So you need to know, what kind of electric service it is, how we come into the building. You're usually responsible for providing, this component, and the utility, doesn't want you. The utility will hang the transformer and perform the wiring up to at this point of connection. So the neutral conductor is the conductor connected to the neutral point of a system that is intended to carry current under normal circumstances. So what we remember is alternating current goes back and forth. The electron just kind of wiggles and generates energy. And when the electron is going from its positive state to its negative state, the point in the middle is a reference voltage of 0. And so what we have is a point on the conductor that has no voltage, which is like a seesaw between two legs that do have voltage. And remember, voltage wants to flow to a lower voltage. And so what happens as we have two, let me see if I can draw this. Let's see, pen. All right. And so we have two legs of our electrical power, and they have loads on them that are turning on and off. And as these loads draw current out of each leg, the voltage is going to start to drop. and then we get into a point where the voltage levels on each leg, one might be higher than the other. And what happens is voltage is going to recirculate through that neutral wire. And so even though it's neutral and we say its reference voltage is 0 voltage, that doesn't mean that it's incapable of carrying current. Instead, it serves as a balance between the two circuits, such that if one leg is imbalanced than the other, it helps stabilize the voltage and maintain the voltage of both circuits at 120 volts. So when we look at this wiring diagram and we're trying to decipher, what is special about a 120 volt or a 240 volt electrical service, what we have here is on the left is a 120 volt electrical service where we have a neutral wire in white and a power wire in black on a circuit breaker. And then we have our green wire, that's ground. And so on a 120 volt circuit, you might be used to seeing a white, black, and green wire. One's your ground, one's your neutral, and one's your black. And what we see here is that there's a reference, a load that has some resistance, like a heater, your computer, whatever electrical device you have. And that voltage flows down to a 0 point. And what keeps that neutral then at its 0 point? Why doesn't the voltage rise on the neutral? Well, at one point on that system, the neutral is connected to ground. And so while electricity is a little bit hard to conceptualize, think about the neutral line as kind of being the drain between two sinks, and that if you fill one sink up with water and you try to drain the other, it might flow back into the other sink. And eventually it all drains out the neutral. The neutral stays anchored to ground, providing a 0 voltage reference point. And in a single phase system on one leg, we have the power on that leg connecting the 120 volts to a 0 volt, and that electricity flows through our device and powers it as it's going to its 0 voltage. Then we get to a 240 volt electric service, like your washer and dryer service. So this is, we still have a black, a white, and a green. So we still have a neutral, a ground, and a power cable, but this might be just kind of exactly like the 120 volt surface. It just might be 240 volts to neutral instead of 120. So you might get a 240 volt circuit that is not split phase. You could only pull 240 volts off of this one leg of power. And so what you have is, if you have a 240 volt circuit run out to your washer and dryer, you can't just wire up a 120 volt circuit off of it. You might have to have a separate transformer that steps it down, from 240 volts down to 120. What 120 volt split phase is you have actually a leg 1 of power. Let's see, a leg 1 of power, and then you have a separate leg 2 of power plus a neutral in the ground. And so the neutral is still connected to the ground at that one point in the system. Then the difference between 120 volt split phase and 240 volt single phase is that now we have a leg 1 of power and a leg 2 of power being balanced by the neutral in kind of that seesaw position where the neutral takes care of any mismatch and balance between the two legs. And then sometimes there's a concern about your loads being mismatched, because what that means is when your loads are mismatched, you're going to have more current kind of flowing through this neutral line. You know, the neutral kind of representing the difference between leg 1 and leg 2. And so if these are not equal to each other, if the load is not matched, you get you know, somewhat of an energized neutral flowing to ground, draining that current out and keeping the voltage stable between the two separate legs. That means that the neutral is not just sitting there connected to ground at 0 voltage. That means that there are many times that the neutral line is carrying current in your home. In fact, it's designed to carry current. In fact, in a solar array, that neutral must be sized to be the same size as your electric load, as a continuous load, but not on all homes do you have that same continuous load, and so they might undersize the neutral. All right, so here is there's a 120-208 electric service, and 277-480 is another common electric service. And so what we might have is point to point in 3 different phases, and the phases, instead of being you know, just complete equal opposites of each other. When you get into commercial design, the kinds of transformers, you get a little custom fit to purpose. You know, maybe you don't need as large of a transformer and you're going on a 240, 208, 3-phase service where instead of, you know, depending on how they wind the transformer, they're handling 3 legs of power in a way that is a little bit more balanced for higher demand users. And I think that there may be some efficiencies gained in 3-phase, not necessarily efficiencies in the traditional sense. 3-phase might be, and I'm just guessing, I don't really know, but 3-phase might be a little bit less efficient than 240 split phase, but it also has what's referred to as rotational inertia, which goes back to how the coils on the transformer are wound. And it seems that 3-phase circuits are more suitable for motors. And you can have high motors and low motors, and you can have high 3-phase voltages and low 3-phase voltages. And the winding of the transformer also varies from type to type, to where you have maybe a Y formation versus a delta formation, and it all has to match. You know, a motor has to have the same kind of electrical service because its internals are geared up for this particular type or that particular type of electric service as well. And to complicate matters further, you still may be able to derive 120 or 240 volt circuits off of a 3-phase service, depending on what legs you plug into and what kind of electric service you have. Make sure, especially when you're just venturing into commercial service for the first time, to note exactly what kind of commercial electric service you have. You know, here we have a 480 277 voltage, and it says it's found in lighting and parking lot light circuits. And to me that makes sense. Maybe these parking lot lights don't use a lot of power, but you're going over a longer distance. So, you know, what might not work at 208 volts, maybe they need a little bit longer voltage per leg just so that they can get further out into the parking lot. So that alone might drive a custom transformer type. And we see National Electric Code trying to rein it in by just saying these are the standard transformers that we use. You may go into a different country and they're on a completely different standard. In the solar industry, we are used to putting warning labels and warning stickers on our equipment after the install. You know, solar design is somewhat custom specific to the job site. And so on our warning labels, we will be writing numbers like voltage and amperage onto the warning labels themselves. You can precisely calculate the information that you need Here in National Electric Code, we keep things a little more simple. It says calculations are permitted to be rounded down to the nearest whole amp with decimal fractions smaller than 0.5 dropped. So I don't exactly know what this means. Got rounded down to the nearest whole amp. So if I have 8.7 amps, is that 8 amps? Is it 8.5 amps? I guess this slide here is replicating code verbatim, but basically what it says is on your placards, you can use whole numbers. You don't have to carry out your amperage and voltage precisely, provided that you're in the range of whole numbers. We've built in a lot of safety factors into National Electric Code. By the time you get into calculating the very last amp of the system, you know, just round down to the nearest whole number and be done with it and move on with your life. So then we have different branch circuit calculations with specific rules for calculating loads of these branch circuits. So there are some kind of standard rules for how much power to allocate for certain kinds of electrical appliances. So if you're building a tiny house and you want to have a well-sized electric panel, a code-compliant tiny house, you might find that you have to go into this section and calculate a dryer or a motor load of National Electric Code. Now, you could also get an electrical engineer to review it and go by an engineered calculation and not necessarily use these code bys. Loads for additions to existing installations. So if you're building a structural addition to your house, if you're putting an inductive range, adding it onto the kitchen, there are some minimum amperage requirements to explore. We get feeder and service load calculations, and this was pretty interesting. The minimum load of a feeder or service is the sum of the loads determined by Part 2 after any applicable demand factor is permitted by Part 3 or Part 4 or required by Part 5. What that says is there is a minimum load that you can design for a dwelling unit. Now, if you calculate all those appliances, you get to your dwelling unit, and the minimum load for that service is determined by rules and regulations and not necessarily your individual client's electric use. And so you might find that, your client only needs 10 amps of power, and a Tesla Powerwall is 10 amps of power. So you might design a tiny house that only has 10 amps of power draw for your crazy customer, and you might not pass inspection simply because the National Electric Code does not deem it suitable for habitation because you're being energy efficient with your dwelling unit. And so for some issues of code, or if you want to be a little out there with your solar design, it all goes back to the authority having jurisdiction. Remember, National Electric Code is not a public document. It's not intended to be a design specification, even though your city may mandate compliance to it. There is an authority having jurisdiction that can supersede code, requiring additional items beyond the minimums established by National Electric Code. And if you ever find a jurisdiction that is not abiding by National Electric Code, usually there has to be a very clear reason why. It's very rare for that to happen. They might not follow code out of ignorance. Code is a big book. And so you might be designing a tiny house, and it might only need a 10 amp electric service panel, and they could look at that and say, okay, well, you're nuts, but have at it. And how do you know who is the authority having your jurisdiction? You can use the Desire website. You can pull up the interconnection standards, rules, and regulations for a given state, and that will pull up the Public Utility Commission, and then you can bother them about it, and they will refer you to, who the distributor is in the area. Sometimes when you're dealing with interconnections, you deal with the state directly for your interconnection applications, and other times you deal with your electric provider. Sometimes you don't deal with your electric provider, but you deal with a grid distributor. So it might be confusing if you're in a new area of who exactly you should contact. Your authority of having jurisdiction can be tracked down. Feeder and service load correction factors. There's correction factors for all kinds of appliances. There's a fixed electric space heating exception that says rather than being calculated at 100% of the load, when you're managing your energy, the local AHJ can allow feeder and service conductors to have ampacity less than 100%, provided the conductors have an ampacity for the load so determined. The larger your home, the more appliances you have, the greater the discount factors can be applied. And so if you're operating, say, a laundromat, they will assume that a certain number of your machines are not operating all at the same time on their maximum cycle. So then we get to the load on the neutrals. The maximum unbalanced load is the maximum net load between the neutral conductor and any one ungrounded conductor. So the maximum amplitude of the largest load on any one leg is considered to be the maximum size of the unbalanced load. And what that means is, when you have unbalanced loads, the neutral may not be able to be undersized. If the maximum size of the neutral conductor is the maximum net load between the neutral and any one ungrounded conductor, all the other loads could be off, and that one ungrounded conductor is at its max load, and the max load would be the potential difference between the ungrounded conductor and the neutral conductor. That would mean that the neutral conductor would have to be the same size as the ungrounded conductor. But the National Electric Code is within reason. It says permitted reductions of the neutral, and so there will be a list of factors of when you can undersize the neutral, and then there are restrictions on when you can't. And you have to assume that the maximum unbalanced load is the full size of the maximum load on that one leg. And so for now, let's just assume that we're not undersizing the neutral. But if you need to have a full-size neutral and you don't, that could be a costly mistake. And then we get into dwelling units. There's optional ways to calculate the loads for dwelling limits. You got general load of 10 kilowatts plus 3 watts a square foot times 30% for lighting. Then 1.5 kilowatts for every 20 amp branch circuit. And then 100% of the load for appliances, cooking equipment, dryers, water heaters, and motors. And that actually adds up pretty quickly. Tankless water heater can be 20 kilowatts of load. Every branch circuit on a home, let's say you have 10 branch circuits, and then you have maybe 30 or 40 kilowatts of appliances, quickly over 50 kilowatts. And a 200 amp electric service, how many kilowatts is a 200 amp service? Residential, a volt times an amp is a watt, and so 200 volts times, or 240 volts times 200 amps is 48 kilowatts. So most homes are going to be 48 kilowatts or less. So this is a pretty aggressive calculation, and that's just general loads. Then heating and air conditioning is based off the maximum use case of the load, whichever one you're using the most of. If it's heating, if you're up north perhaps, if it's air conditioning, if you're in the south part of the United States. And then if you have multifamily housing, the homes are considered to be more energy efficient, And of course, you have the individuals in that home using the electricity at different times. And so you get additional discount factors for multifamily housing. And not just for dwelling units, but schools and restaurants, farm operations. There's guides in code, and as well as on other government websites like EIA.gov that can help you size electrical loads or estimate electrical loads for new construction. Of course, anyone will tell you nothing's better than actual hard data. You can use the actual maximum demand on the existing load under certain conditions. If it's a 1 year period, and B, if it's not in a 1 year period, what's your maximum 15-minute demand during the highest load over the past 30 days, which of course that's not nearly as accurate. So there are allowances on sizing new services based on your existing loads. If the client is building a new home and it's the same size or often smaller than their existing home, and it's more energy efficient than their existing home, and you have a 24-hour a day, 365 day a year map of their current energy use, and if there is usually it's an electric vehicle, you can model that impact. Sometimes when you have a solar rebate program, in order to do your array size, they're going to look at your maximum home's load. And it might come back that your home only uses 14 kilowatts of power, and so you can only have a 14 kilowatt array on your rooftop. And you say, well, wait a minute, I have a 48 kilowatt electric service panel. And they'll say, well, your demand never gets that high. And you can say, well, hold on a second. And you go and you turn on all the appliances in your home, and your demand will surge up to 40, 45 kilowatts. And so I want to do that largest array I possibly can. What's the difference between a hutch and a building? The building has approved firewalls and fire doors. A garage is a garage a building. It's a building or a portion of a building in which one or more vehicles are kept. So yes, a garage is considered a building. Bonding, connected to establish electrical continuity and conductivity. The bonding jumper system, the connection between the grounded circuit conductor and the supply side bonding jumper, or the equipment ground conductor, or both at a separately derived system. Okay, bonding is electrical continuity. Put electricity into one stick of metal that's touching another stick of metal, I'll pick up voltage on the other stick. And the reason why that's important is sometimes metal can touch metal and it's actually not bonded, because to fight corrosion, we'll give it a protective anodized layering. And one of the effects is that anodized layering is not as conductive as the interior of the metal. And so if you take one piece of metal with an anodized coating and another piece of metal with an anodized coating and touch them together, there's a lot more resistance between that metal than otherwise, and it's not considered a ground path. It's not considered to be a point of resistance. If it became a point of resistance, it could get too hot and cause a fire. The bonding jumper system refers to the connections between the grounded circuit conductor, the neutral wire, and the supply side bonding jumper or equipment grounding conductor, or both at a separately derived system. Okay, what does that mean? The supply side bonding jumper protecting the service. So you open up your electric service panel, you see that big breaker there. The side with all those little breakers is your side, the load side, and on the other side, that's the supply side. So we're talking about a supply side bonding jumper that connects the grounded circuit conductor to the equipment ground. So remember earlier we mentioned how the neutral is somehow connected to ground. Well, that's part of the bonding jumper system. Where the utility will connect the neutral to ground is part of the bonding jumper system. Here is the high voltage power lines with a neutral, and that neutral is going into the transformer, and the transformer is also establishing a reference voltage to ground and providing a leg 1, leg 2, and neutral at the meter. So the utility is providing the neutral, and the utility is connecting that neutral to ground. Here's where you might have a connection between two pieces of metal on your racking system. And we have an anodized stick of rail and another anodized stick of rail. And even though they might be butted up together, metal touching metal, it's not considered grounded. This is a metal roof. We have a metal attachment point. But if we don't use a metal grounding screw, it's not considered grounded. And in fact, we don't even need to ground it because what we're doing is grounding the railing above it. It's probably better if we don't ground the footing. We make sure that our ground path goes from our rails directly into our equipment ground conductor. Now, sometimes the metal roof can be used as an equipment ground conductor. I don't really like that concept so much because I'd rather control where the electricity goes than spread it out over a surface where who knows what could happen. So coming back to this one-line diagram, what would be considered the bonding jumper system? Where is the bonding jumper? Where is that neutral connection being made to ground? Here we have the neutrals all being bonded together. Where's the neutral connecting to ground? Well, it can be at the transformer, up here on the power grid. That could be connected to ground. Or you could have a separate neutral for the power grid and the generator, and you switch between the two, but you're always connected to one or the other. On an automatic transfer switch, you would need to be able to reference both to be able to run the switch. And so if you have a grid connected system, the bond is coming in from the utility. If you have an off-grid system, you need to create your own. But you can make a mistake if you're creating your own bonding jumper to ground, and you're supposed to be using the utility bonding jumper as your point of reference. Substation. An enclosed assemblage of equipment, switches, circuit breakers, buses, and transformers under the control of qualified persons through which electric energy is passed for the purpose of switching or modifying its characteristics. And so the substation is a component on our electric grid that will take, higher voltage transmission lines and step them down into those medium voltage transmission lines that might serve distribution circuits that will step down to, our 2400 kilovolts, which will then step down to our 240 volt services. So substations, you can see the high voltage power line footing here, and then lower voltage coming off of it as well. Outside branch circuits and feeders on or between structures or poles. Equipment and wiring for supply equipment outside of the buildings. You're allowed to run branch circuits and feeders outside of buildings. There are rules for offset space requirements. Table 225.3 is a list of all the other articles that have specific rules and regulations to branch circuits and feeders of particular equipment, such as communication wiring or fire alarms, emergency systems, and of course solar power gets its own section too. So this is kind of like the table of contents for National Electric Code is in 225. I think of a National Electric Code almost like a piece of computer software that writes itself, where right now it's talking about how power gets into the building and the appropriate sizes of the conductors, and now it's saying, and there's special rules for these kinds of equipment, and here's the sections where we're going to discuss it. Let's define a raceway: an exposed channel of metal or non-metallic materials. So a raceway can be metal or non-metal, designed expressly for holding wires, cables, or bus bars. You know, it has to be listed for purpose, or if it's not listed, it's not saying a raceway needs to be listed. It says it just needs to be designed expressly for the purpose of holding wires, cables, bus bars, with additional functions as permitted in this code. So, you'll have to look up whether a raceway is listed or not. Since I can't teach the actual code, I can't let you know. So you need to go buy your code and check that out. This is a typo right here. Huh, that would make a good quiz question. Raceways are enclosed. Enclosed. And so the problem is, well, is a piece of unistrut considered a raceway? You know, unistrut is like a metal channel, and then it comes in a long bar. Usually it's more rectangular than this. It has little slotted holes inside the channel that you can bolt things to, and it's open. So you could say, well, can I just put my solar cable or my electrical cables down this unistrut and use the unistrut as a raceway? Well, this is saying no. It says that raceways need to be enclosed. The definition of enclosed is surrounded by a case, housing, fence, or wall that prevents persons from accidentally contacting energized parts. So I guess we're still looking at, would unistrut be considered enclosed or not? Maybe we'll have to get further into code before we can interpret that. So a raceway is an enclosed channel of metal or non-metal materials designed expressly for holding wires, cables, or bus bars with additional functions as permitted in this code. And then the definition of enclosed is surrounded by a case, housing, fence, or wall that prevents people from accidentally contacting the energized parts. So raceways need to be enclosed. Raceways need to prevent accidental contact from energized parts. Now, a ground fault occurs when there's an ungrounded conductor. So that's a hot conductor that's full of voltage. And then you have a normally non-current carrying part. And so there's accidental connection between an energized cable and a metal part or earth. So remember, earth has this reference voltage of 0, and your ungrounded conductor is full of voltage. And so just like water in a bucket at the top of the mountain, if there's a way for it to flow into the bottom of the mountain, you tip that bucket over, you make this electrical conducting connection. That's a ground fault. And when you take a live electric wire and you touch it to the ground and it snaps, and don't do that, but that's a ground fault. An arc fault is a little bit different. An arc fault is when you would, and don't do this either, but take a live power line and snap it off with your wire cutters, and then you pull the wire apart and watch that pretty electricity kind of jump across the two wires. And you're like, wow, before you die. That's an arc fault. A ground fault is when you're touching one end of those live conductors to ground, when you're going from 240 volts to 0. And a ground fault circuit interrupter is a device intended for the protection of personnel that de-energizes a circuit when the current to ground exceeds a specific value. Well, what on earth are we talking about? Well, like a breaker. A breaker, a 20 amp breaker. The current exceeds 20 amps, it switches. A fuse. The fuse exceeds 20 amps and it burns itself up and it opens the circuit. Then we have an arc fault current interrupter, a device intended to provide protection from the effects of arc faults by recognizing characteristics unique to arcing and de-energizing the circuit when an arc fault is detected. And that's, arc faults are a little bit more insidious than ground faults. With a ground fault, you have a lot of voltage up at the top of the mountain, and then you have no voltage at the bottom of the mountain. So when that bucket spills over, it's going to all rush down the mountain and produce a lot of current and be detectable. Arc fault current interrupter is when the voltage is just at an open circuit, but the circuit isn't supposed to be open, it's closed. But instead you just have two wires just kind of touching sometimes and not touching sometimes, and there's a little arc that will go across the wires, almost like static electricity, but sustained. And static electricity would be more of a ground fault than an arc fault. An arc fault would be if you pulled your fingers apart and still got shocked, where the voltage is, there's enough, there's not enough resistance to interrupt the flow of the voltage. You might get some kind of plasma stuff being occurring, but you'd have to get into the physical details with an electrical engineer. But arc fault detection is much harder than ground fault, and these are relatively new. Nowadays, most inverters will recognize arc faults, and it's interesting that previous iterations of inverters did not detect arc faults, and now when I turn on an array, I'm used to having my owners say, well, I never have any kind of maintenance issues, but I've already had one owner with an arc fault issue, and it's changed my whole line of thinking on solar array maintenance. And it's since then I've confirmed it with other installers. The number one failure point in a system is in that homemade connection, that MC4 connector that you homemade at the end of one circuit that comes back to your inverter. You're building a custom cable. Most of the time you're building that custom cable on site, and if it doesn't get made up tight, if it doesn't snap in correctly, then what's going to happen is that connector gets plugged into the system starts up, and maybe it's connected today, but after 2 months in the field, that loose connection works its way out, and now the connector no longer is making solid contact, and maybe it's conducting electricity, maybe not. Well, it used to be that inverters would just ignore that problem, and that's a safety risk. You have a loose connection on your system, it needs to be addressed. But you also had this effect of now there's a little bit more maintenance to perform on the systems, and that's a good thing. I don't think it's wise nowadays to be advising customers that there's zero maintenance with solar. You want to train them to expect maintenance, and then when maintenance does occur, they're not upset. Well, and additionally, there's a separate issue with old school inverters involving ground fault detection. And let's just read the description for a minute describing the Dietz-Watson warehouse fire in New Jersey. So you can read the whole article on Solar Pro, great magazine for solar professionals, obviously. But as an MC4 connector sat in a puddle on a commercial rooftop in New Jersey, a fire risk was developing. Exposed to harsh winters and humid summers in the 6 years since its installation, the seal had broken down and was now providing a hazardous path for the DC current to Earth. So imagine you have a puddle and you have a circuit, and the solar conductor is now dropping down in that puddle. And now your puddle is energized. But it's not connected to ground. Water on top of a TPO rooftop, that TPO rooftop is insulated. So now you have a ground fault on the ground. And where can that puddle occur? Well, it can occur inside your combiner box. You could have a loose connection come out, and then you could have condensation coming up and creating a puddle inside your combiner box, and you get some condensation in this combiner box. If the water gets high enough, there you go. You don't even need to have a fault in your wiring if your combiner box fills up with water. And so some of the lessons learned about ground faults, and the problem is with old school kinds of inverters, they would read the reference voltage to ground of the inverter and its ground fault detection system. They would take the negative reference and attach it to ground and say, what's the difference between the two, and any difference would trigger the ground fault detection. Well, the problem is now the array is already faulting into ground. And so when the array turns on in the morning, the ground voltage rises along with the solar array. So all of a sudden you have an indetectable ground fault of ever increasing amperage and set the building on fire. So for best practices of reducing ground faults, you can use shorter circuits. You can avoid conduit bodies for 90-degree turns. Don't shove all your wire into a protective sheath unless you have to. Avoid the need for expansion fittings where the wires could be caught and frayed. You could I don't really know if you'd use aluminum for larger circuits or not. But then for arc faults, it's more of a workmanship issue, where if you're using brand new to solar installers on your installs, the wiring work is the last thing you want them to be doing, because they're not trained for that. An electrician's gonna have much more respect for making a connector up tight. So that's where the real hand skills is not just knowing how an MC4 connector is made, but the craftsmanship of being able to get every single connection on the job site correct. Article 225, outside branch circuits and feeders. We have 225.10, wiring on buildings. The installation of outside wiring on surfaces of buildings shall be permitted for circuits of not over 600 volts nominal. So here's the infamous 600 volt limit on the outside surfaces of buildings. And so we say outside on the wiring of circuits of buildings, we can't be over 600 volts nominal. And we get a variety of rules shortly thereafter governing how wires outside of buildings enter and exit buildings. So wherever branch circuits and feeder circuits leave or enter a building, there's certain provisions that we haven't gotten to yet that are referenced later on in code. Then if we have open conductor supports, there's actual spacing requirements. So when you're supporting your conductors in conduit up on the rooftop, there are spacing requirements for the supports, the actual conduit support blocks. Supports over buildings, attachments to buildings, and clearances for overhead conductors and cables. Depending on your usage and depending on the usage of the roof itself, there are different height requirements. So you might be thinking, well, can I go overhead with this particular wire run? There are rules in code for that. Amazing, but true. Article 225, outside branch circuits and feeders. Above rooftops, you have to have a 8-foot clearance for a distance of not less than 3 feet in all directions, except where the roof is subject to pedestrian traffic, like a rooftop swimming pool or a rooftop deck, at which point you need to be much higher than that. I'd say 18 feet, most likely. The final span clearances from open windows, doors, porches, balconies, or similar locations is 3 feet, unless you're at the very top of the building. And so if you're at the very top of the building, you can just stay to the side of the building and go over the top. So, essentially, you have to be 3 feet away from all objects, except there's an assumption that, you're going to stay on the same plane of the building, and the very top is what's considered, out of harm's way. Of course, again, minimum safety standards. So if you have a rooftop porch or whatnot, going over the top of the building would not be as safe as, say, going back into the building. Mechanical protection of conductors. So on buildings and structures and poles, you need to have mechanical protection of your conductors. And so, like solar conductors can be open air, but that's only inside of the solar array. Outside the solar array on the rooftop, they need mechanical protection. And, when you go inside the building, you still need mechanical protection. In fact, your mechanical protection gets even harsher. They say you need to be in metal conduit. So, metal providing a little bit more protection than PVC. And you can be in PVC up on the rooftop. You can't be in PVC with at least DC wiring inside the roof. So there's certain rules for multi-conductor cables on exteriors of building surfaces, for raceways. The main thing is your raceways need to be arranged to drain, and they need to be suitable for wet conditions. And then we have a raceway seal requirement. It says whenever a raceway enters a building or structure from underground, it should be sealed in accordance with a section we haven't gotten to yet. Spare or unused raceways should also be sealed, and sealant should be identified for use. And what's the big deal about raceway seals? Well, the exterior is a wet location, and inside the attic, it may be considered a dry location. But if there's a hole in your roof, between your roof and your building, then water can get into the hole. And you might say, well, I have a NEMA 3R combiner box. And NEMA 3R is water and rain resistant. So I don't need to worry about that on NEMA 3R box. So I'm going to skip over the raceway seal. Well, the problem is, if you're in a humid environment and you have cool air inside the building or below the conduit and warm air up above, you're going to get condensation occurring inside your conduit. And so I've made this mistake before. We had an underground service entrance conductor coming up from the utility and then going back down into the ground. We had the underground service connection coming in from the utility, and then we had power going into the home, and then we did a line side tap to stay outside this guy's log cabin. And from the line side tap, we just went up straight into the soffit of the attic. Well, the humidity and the heat difference between that underground utility service entrance run and then going through the outside porch up into the attic, and then from the attic, I guess we just went into the attic at that point. But that was enough to cause a puddle of water to occur in our junction box where we made the line side tap. So what we had to do is not only drain a little weep hole into the box, but then we also had to seal up the conduit to stop the condensation. Wherever there's a temperature differential, from the roof to the attic, from the outside to the inside, you need to seal the insides of the conduit. Conduit is not designed for you to put wire into and then pull the wire out of, and for you to put the wire back into it. It's not that you can't do that, but whenever you are doing it, it's because someone messed up the design, and it's a very expensive process. And you can't always do that. Maybe the conduit path raceway has broken inside whatever building or structure you built. So a conduit is not designed to be two-way, in other words. The number of supplies. A building or structure that is served by a branch circuit or feeder on the load side of a service disconnecting means shall be supplied by only one feeder or branch circuit unless specialty conditions such as fire pumps, emergency systems, standby systems, parallel power production systems. All right. Solar power. That's us. Systems designed for connection to multiple sources of supply like batteries or generators. And then special occupancies by permission for multiple occupancy buildings where there are space restraints. So like if you have 50 people living in a tiny building, they may allow you to have more handles than this. When it says a building shall be supplied by only one feeder or branch circuit unless special conditions apply. And so that special condition, we could also supply our buildings with an on-site solar array in addition to the utility circuit. So it's one supply from the utility unless special exceptions are made. Additional feeders, here's some special exceptions. Additional feeders where the capacity requirements are in excess of 2,000 amps at a supply voltage of 600 volts or less. And so this is, when it says capacity here, capacity requirements, they're talking about amperage. You might get a 240 volt service at the commercial level. You might get a 480 volt service, twice the voltage. And so a 2,000 amp service at 208, often at that point they'll just say, oh, you go up to 480. Well, then you get to 2,000 amps at 480 and they say, all right, you're using a lot of power. We're going to put an additional feeder onto your building. Well, how much is that? 2,000 amps times 208 volts, or let's 480 volts. That's almost 10 megawatts of power per service. So when you get into extremely large capacity requirements, you're dealing with a lot of power. And in fact, I had a conversation with a solar installer who was trying to research net metering policies. And he said, I have a building and the capacity of the building is huge, but the energy use is really low. And so we want to put all the solar arrays onto this building, but we want to tie the array into the small parking lot meter that is on an energy only rate, because we have 40 other accounts throughout the city that are on energy only rates. And so, we want a net meter at the energy only rate, not at the demand charge rate. And I thought he was kind of being a little wishful thinking, because I couldn't imagine if you do have a utility demand charge that the utility actually signing off with you kind of playing, 3-card Monty with your electric services and virtual net meterings. But what he said was not that his building had big demand requirements. It's that his building had big capacity requirements. So capacity is often referred to as the megawatt rating of the system. In fact, the term capacity factor is a percentage that says what percentage of the year is your generator operating at full capacity. You know, solar being on for 4 to 5 sun hours a day, 24 days out of the year, you're looking at, around 1/5 of the hours at most, and you're looking at, a sixth to a fifth. So solar capacity is 20% at the most, and usually it's more like 15% capacity factor. You have a disconnecting means. Means shall be provided for disconnecting all ungrounded conductors. So not the neutral, all ungrounded conductors that supply or pass through the building and structure. They're not saying a knife switch. They're saying a disconnecting means. A switch, a breaker on your service panel is a disconnecting means. Disconnecting means shall be provided for disconnecting all ungrounded conductors that supply or pass through the building or structure. Location shall be installed either inside or outside the building structure served or where the conductors pass through the buildings. The disconnection means shall be at a readily accessible location nearest the point of entrance of the conductors. For the purposes of this section, the requirements of 230.6 shall be utilized. This is a controversial section, because what it says is the disconnecting means should be readily accessible at the point of entrance of the conductor. So it's, are you supposed to have it inside the building? Like, let's say you have your inverter and you have the option of mounting the inverter inside the garage or outside the garage. But inside the garage is a cooler space than outside, and so you want to put the inverter inside the garage. Have less dust, less debris, better air-conditioned environment, longer life out of the inverter, whatever. You're putting the frickin' inverter inside the garage. Okay. Well, so now it comes time to service the inverter, and you want to turn the wires off inside the inverter, except they're hardwired to your array up at the top of the roof. And so while you might have a disconnect in the inverter that would be code compliant, it doesn't do you all that good unless you can access the non-disconnected section. So sometimes you get a external disconnect on the inverter that's built into a separate housing compartment than the rest of the inverter system. So you're not unwiring the entire inverter and the entire solar array to service inside the inverter. So that's a pretty good feature. So you would want the disconnecting means to be next to the inverter so you could just go up to the inverter, flip the switch, and service it. But really what the utility wants is the switch to be outside the building, because what they're concerned about is being able to easily turn the system off if there's an emergency. And so, basically where this boils down to is no matter where you are with solar, your utility is going to want to see an external disconnect switch at the point of entrance where the power enters the property that can turn off your solar array, so that when they're pulling your utility meter to turn power off to the property, they can also flick your solar switch and turn the solar array off as well. They're not as concerned about you having a switch inside your garage to access, although that might be convenient for your customer. Utilities want this external disconnect switch to be right by the point of entrance for the electricity into the property. So for this discussion, we needed to talk about what the definition of accessible is. Now you have switches that need to be accessible, switches that need to be readily accessible. And then we have accessibility with regard to equipment, and then we have accessibility with regard to wiring. So accessible is admitting close approach, not guarded by locked doors or elevation or other means. Accessible for wiring methods means capable of being removed or exposed without damaging the building structure or finish, or not permanently closed in by the structure or finish of the building. So accessible by wiring methods is, can we open up a box and access the cable splice, or is it completely sealed into the building? And then we have readily accessible, which is capable of being reached quickly, without requiring those to whom ready access is required to climb over or remove obstacles. And that becomes a little bit tricky because your roof-mounted combiner boxes need to be accessible, but they don't need to be readily accessible. What they want for that disconnect switch is for it to be readily accessible. Then we have in sight from or within sight. So where this code specifies that one equipment shall be in sight from or within sight from, and so on and so forth, that should be a distance that's visible for no more than 15 feet. And so, I don't recommend this, but let's say you have a ground mount array and it's out in the array, and then you have your inverter that's on the side of the building. And let's say your utility is requiring you to have a separate, and let's say you just want to take your circuits from the ground mount and you want to run it right back to your inverter. Well, you don't need, if the inverter has a DC disconnect switch built into it and you can see that inverter from the ground mount 50 feet away, you don't need to put in another disconnect switch. If that disconnect switch is within sight, then you don't have to repeat the disconnect at both ends. So you could just get away with locating the disconnect at one end. But, again, when it comes to minimizing disconnect switches, you have to think about it in terms of serviceability. Just because you're not required to have a disconnect at the edge of the array doesn't mean that you shouldn't have a disconnect at the edge of the array, in terms of a serviceability point. Then again, you don't want to do overkill, because every time you splice a cable, you put more resistance into the system. Utilities would do themselves and the solar industry a favor by understanding the definition of a disconnecting means. Disconnecting means can be a breaker. It doesn't have to be a knife switch. Often utilities require knife switches, which are more expensive than breakers and not necessarily any more useful. I suppose the knife switch is something that can be viewable from a distance, and you can open up and inspect the disconnect switch and see that the knife switch works. I guess a breaker could fail. But code only requires breakers to serve as disconnecting means, and that could, your utility may or may not require a knife switch disconnect to complement the breaker on your electric service panel. And these disconnects for feeders shall be installed inside or outside the building or structure wherever they pass through the building. The disconnecting means shall be readily accessible at the nearest point of entrance. So I suppose if you had the most persnickety inspector in the world, they might want you to put a disconnect at every location every time any power line goes through the building. That's not been my experience. The utilities just want to see that external disconnect outside the building right next to the electric service. So you say, well, wait a minute, how many disconnect switches can I have next to each other? And the rule of thumb is 6. You can have 6 disconnecting means for each supply at each service entrance conductor. And that's interesting. What happens if I have more than 6? Well, if you have more than 6, then you need to have a main breaker that operates all of them at the same time. So you'd wire them in parallel and have one big switch at top, which is exactly what your electric service panel is. It's, a number of circuits wired in parallel with one big switch on top. And so when we're talking about grouping these service disconnects, what we're saying is you could have a service disconnect that's one main breaker and dozens of sub breakers. But if you only have 6 circuits that need power supplied, you don't need that main breaker. So you get into service equipment that's called main lug only. And that's where if you have distribution circuits throughout a building or complex, or even coming into the property itself, if there's 6 circuits or less, they may just avoid buying a main breaker. If you buy that main breaker, no skin off your back, it might make the service panel a little bit easier to wire and service, and many electricians will order that if they have the budget to, but you don't need it to be code compliant. Where are these disconnects grouped? They need to be marked to indicate what load they serve. Additional disconnecting means can be required for special cases, but if they're for standby generators or emergency generators, the disconnects are required to be remote from normal supply. And this, I think, is a pretty pertinent code for battery backup systems. Is that the problem is, what if you're the city of Houston just flooded? So what if you're the fire department and you pull up to a house and it's on fire and it's flooded and the electricity's still on? So you run and you yank the power to the property and turn it off. Well, what if your standby system then kicks on? Well, you need a standby switch. Well, what if the standby switch is powering grandma's respirator and it's there for an emergency rather than just a backup? And so the fire department, turns off grandma's respirator when they're trying to save her. So there's some, we need to give some more thought to emergency disconnect locations. They need to be clearly marked and labeled. And while they need to be away from the normal building, I would think they would still need to be within sight from the normal building with a placard, just to indicate to the first responders what exactly is going on and what switch does what. There's a third-party switch you can buy. Midnight Solar makes it. You press the switch, that de-energizes everything. Your solar rapid shutdown, your battery breakers on the service panel. The whole system turns off. And, that might become more of a mandate in the future, where we start to see philosophies and rapid shutdown for solar start to be applied to battery banks and stuff like that. But then again, having one switch that de-energizes everything in a readily accessible location doesn't sound like the best solution either, because now you could have pranksters come around and easily power down your whole building, and that's not suitable for safety for that matter either. Where the design is going to end up, I don't know. Identification: where a building or a structure has any combination of feeders, a permanent plaque or directory shall be installed at each disconnect location, denoting all other service feeders supplying or passing through that building, with exceptions for multiple connected dwelling units and industrial buildings. So every solar array has multiple feeder circuits, and so a plaque or directory describing all of the other services should be on that building. So you get concerned about labeling requirements in solar. Well, here's another label for everyone to worry about. We got disconnect locations. They can be manual or power operated, as long as they can still be operated by hand. So you might have, I know Outback makes a motorized circuit breaker, and so does Schneider. And there might be reasons why you want to manually lift the breaker open in the service panel. For instance, if you had a generator, a small generator and a large generator, and you wanted to choose between the two based off the power usage of your off-grid home, but that disconnect needs to open up, both poles of the circuit. There should be a means to disconnect the grounded conductor, and it needs to indicate open or closed. And then we have some minimum ratings of the disconnect as well. And this is where let's say you're doing a supply side tap connection. The minimum size of a supply side tap connection is 60 amps. And what we're seeing is a family dwelling has a minimum 100 amp minimum. So going back to that 10 amp tiny home, the Tesla Powerwall only outputs 10 amps. So is it capable of supplying the power for a home? No, you would need 100 amps. You need 10 Powerwalls for an off-grid compliant solar home. I suppose you would just connect it to an inverter instead and step down the voltage and step up the amperage. But one family has to have a 100 amp home, 2 circuits, 30 amps, single circuit, 15 amps, all other circuits, 60 amps. And then there's special rules again for circuits that are over 600 volts. So, then we get into electrically operated disconnecting means, additional rules for isolating switches, more inspections and tests, and clearance requirements. More labeling requirements. So, not just telling where the power enters and exits the property, but here is, for substations, a permanent legible single line diagram of the station switching arrangement, clearly identifying each point of connection to the high voltage section, shall be provided in a conspicuous location within sight of each point of connection. So, here we have diagrams. If you're in a high to low voltage electrical unit, you better know at each point when you're stepping up into high voltage what's going on. Each point of connection needs to be visible. And sometimes that attitude just kind of trickles down into residential inspectors' knowledge, where they say, well, your emergency backup system, I need to know that it's there. It needs to be within sight. It needs to have a label on it. They're not just being unreasonable. They're not being unreasonable. Article 230, electric services. It covers the service conductors and equipment for control and protection of services and their installation requirements. So the number of services. A building or other structure shall be supplied by only one service other than those special conditions. Additional capacity requirements where the building is in excess of a 2,000 amp power supply. Where the load is greater than what the distributor can supply, they'll give it some more service, or by special commission. Not that big a deal. One building or structure not supplied through the interior of another. So you can't pass your utility feeder conductors through the inside of one building and out the backside and into a new building. Almost like the neighbor who throws an extension cord over the fence to power his home during an outage. You're not allowed to run power lines through a building into another. Conductors that are considered outside the building are underground, under more than 2 inches of concrete, encased in concrete or brick. Concrete, again, having a very low resistance or very high resistance. When installed in any vault, like an open void of concrete, were installed in conduit and not under less than 18 inches of earth, as opposed to direct buried into concrete, were installed in overhead service masts on the outside surface of the building, traveling through an eave of that building that meets certain requirements. So they say, if you're on an overhead service mast and you stay on the outside surface of the building, but you have to go through the eave of one building to get to the next building. You know, as long as it meets certain requirements, they give you a little bit of allowance. I guess if you're like on a northeast coast style row home. You know, other conductors in the same raceway or cable are not allowed except for grounding conductors and bonding jumpers and load management control conductors having overcurrent protection. What does that mean? You know, what that says is if I'm establishing a electric service on my service cables, and this is not the utility service cables. These are really the service entrance conductors coming from our solar array, which are feeder circuits, you know, or analogous to feeder circuits. If they function the same as feeder circuits, and we call them services instead of feeder circuits, well, what's the difference? They're going to have the same safety requirements. And what this says is other conductors in the same conduit, in the same raceway, in the same bundled cable run as your solar conductors are not allowed, except for your grounding conductors and your bonding jumper system and any load management control conductors having overcurrent protection, which would actually be like you know, a DC power optimizer that directly drives and controls the current, or a battery conductor system would have load management control conductors in them with overcurrent protection. And then we talked about the raceway seal earlier. Clearances on buildings, often 3 feet or greater from open windows, doors, or similar locations. You know, if this feels like deja vu, you're not going crazy. This is the same requirements for services as we saw for feeders. And remember, you know, services is a more specific kind of feeder, and it's coming a little bit later in code. So we've defined feeders that are supplying, you know, service panels, and now we're talking about services that provide and supply power to the building themselves. And, you know, they function very similarly to feeder circuits. They are feeder circuits. They have the same safety requirements of feeder circuits. And so as long as you understand that the power lines need to be 3 feet from open windows and open doors, but then you get to the top of the building and you might only have 1 foot between the top of the window and the crown of the building, and you realize that you can go up and over that 1 foot, it's the same requirements or very similar requirements as to what we just saw. And we're going to see this variant on a theme as we go through National Electric Code. So eventually you'll develop a comprehension, and maybe some knowledge from one section of the code will help trigger, you know, what you're supposed to do correctly in a later section. You know, feeders, services, branch circuits, they have similar protective requirements. So insulation, service lateral conductors shall be insulated for the applied voltage, except a grounded conductor shall be permitted to be uninsulated. Now, service lateral conductor shall be insulated for the applied voltage. So if I have a 600 volt appliance like a solar inverter input from the solar array side, I need to make sure that my cable is rated for 600 volts. You know, electrician cable is rated for 300 volts because they only deal with 120, 240. So 300 volt cable is fine. Although commercial cable on a 480 volt system, they might get some 600 volt cable. And then solar cable is often rated at 2000 volts. So, you know, do I need to use solar cable on a project if my cable is otherwise rated for 600 volts and listed for the environmental conditions of a wet, or listed for the environmental conditions of a high temperature? It may depend on your inspector. You know, if I have a feeder cable or a service cable that is rated for external environments, for weather resistance, for wet conditions, and I want to run it over a rooftop, my inspector won't require me to use PV wire. They'll say, well, we use USE2 wire, and I see you're using USE2 wire, underground service entrance wire, so we'll permit you to do it. In other jurisdictions, they say, no, PV cable is a 2000 volt cable, and USC cable is a 600 volt cable, and we want you to use the 2000 volt cable even though you're only at 600 volts because it's a more robust cable. That jacket is more robust. That's why it can withstand a higher voltage. We want our solar arrays to be more robust than regular design standards, because let's face it, they're going to be subject to the weather and elements and up on the roof for a long time. There's no reason to cheap out over cable jackets when these systems cost tens of thousands of dollars. You can afford a good cable. But there is one conductor there whose job it is, not the neutral. The neutral's job is to provide a reference to ground. So the neutral is grounded, but it's not grounded all over the place. Then it wouldn't be a very good reference. It needs to be only grounded at one point. The utility, more than not, is providing that point. But then there's that green ground cable, that equipment ground conductor that's grounding all your metal parts together throughout the installation. And they say, well, that does not need to be insulated. So some installers like to show off and get a green insulated wire with the ground in it. And that's fine too. Good labeling, I will not speak ill of. That's awesome. But it's often permitted for bare copper to be that grounded conductor and not required to be insulated. But the word of caution, bare copper is not suitable for all soil. So just be aware of that. Aluminum or copper clad aluminum without individual insulation or covering, where, often you're able to choose between aluminum cabling and copper cabling. I only see aluminum being used for very large installations, but I don't think it's substantially more cost effective than copper. Size and rating for your underground services, not smaller than number 8 AWG copper. I think what we're talking about here is still the grounded conductor. Should be not smaller than number 8. Protected against damage, protected in accordance with 305, or entering a building, or protected by a raceway monitoring. Splice conductors, service conductors shall be permitted to be spliced or tapped in accordance to certain sections that we haven't gotten to yet, so we're just going to reference those later. The number of service entrance conductor sets. We already read that you're allowed one set of service conductors to supply a building, unless the building is a multi-family housing project. Or if you have 2 to 6 disconnecting means and separate enclosures grouped at one location, and they supply separate loads from one service drop, then you can have 2 to 6 of them grouped at the same location, supplied from one service drop. So you would have like 6 service entrance conductor sets coming off of one service on 6 disconnect switches. Accessory structures on a single family unit, load management devices, standby power, solar batteries. This is another interesting thing. Your service entrance conductor sets, you get an additional set for on-site energy power systems. Now, if you group these disconnects along with your service disconnects, then that still can't exceed that number 6 model. So whenever you find yourself on a job site and you have to do more than 6 things to completely power down wherever you are, that's the code violation. Installation of service entrance conductors requires installation if entering or on the exterior of buildings with bare copper exceptions. So you need to insulate your wires when you're inside or on the exterior of buildings. So power lines don't necessarily need to be insulated, but your live power lines do need to be. And they're generally sized for 125% continuous ampacity and 100% of non-continuous load. So, all this is not anything that we didn't see in previous sections. Boy, I'm falling asleep teaching the class. You know, code's boring when you get to this part. The minimum ampacity for ungrounded conductors for specific installations shall not be less than the rating of the service disconnect means. So, basically if you have a 200 amp electric service, the ungrounded conductors for... I'm going to take that one out. Alright, so then we get to part 4, service entrance conductors, which governs the sizing of the actual service entrance conductors themselves. So we have the grounded conductors. The grounded conductor shall not be smaller than the minimum size grounded conductor brought to the service equipment. That's the neutral. The neutral wire, the neutral wire, where an AC system under 1,000 volts is grounded, the neutral is routed with the ungrounded conductors to each service disconnect neutral terminal bus. So we have an AC system, our home. It's grounded. Our home is grounded. The neutral wire of the home is routed with the ungrounded conductors, the positive and negative conductors, to each service disconnect neutral terminal or bus. So at the service disconnect, and that might be inside the electric meter, that might be brought out all the way to your, it's where the power enters your property. So it may be further up the utility line than your electric service panel. So you're not connecting in your electric service panel, you're not connecting neutral to ground. But if you're establishing a new electric service, you still might need to provide a ground out by the transformer for the utility to connect into. The grounded conductor shall not be smaller than the minimum size per grounded conductors brought out to the service equipment. The neutral's wire is routed with the positive and negative to each service disconnect neutral terminal or bus, and there it's connected to ground. A main bonding jumper shall connect the neutral to each service disconnect means enclosure. The grounded conductors shall be installed in accordance to these rules and regulations. So here what we see is the main bonding jumper connecting the neutral to the service disconnecting means enclosure. And that service disconnecting means enclosure is made out of metal, and all metal parts are connected to the equipment ground conductor, which is connected to the grounding electrode conductor, which is connected to the grounding electrode. So right here in the service disconnecting means from the utility, the main bonding jumper is connecting the neutral to ground. So where is the neutral connected to ground? Is it connected to ground at the utility service entrance disconnect, or is it connected to ground inside your main service panel? It's connected at the service entrance disconnect. And if that happens to be your main service panel, maybe you have a combination meter base where the meter is inside the service panel and that's the only service panel for the entire system. Waha! Well, that might be the utility service disconnect, but your main service panel is not always considered by the utility service to be the disconnect. Often it will be inside the disconnecting means enclosure, which might be the meter base. In other words, from a solar designer's perspective, now here's our solar array, and it's connected to our grounding electrode conductor system. And we have a DC side, and we have an AC side. And actually, both sides need their own grounding electrode conductor. It gets a little bit confusing, but basically what you're doing is running some bare number 6 up to the rooftop and then tying that number 6 into the grounding electrode system. That's the easiest way to do it. Just run some bare number 6 copper up to the rooftop and then go and land it on your ground lug on the side of the building. There's other ways to do it. Then again, it's like, what's the role of this bare copper wire going up to the rooftop? You know, that role is if there's any voltage on your system. And why would there be any voltage on your system? The only reason is if something's gone horribly wrong, you want that voltage to push its current out through the grounding electrode conductor into ground. You don't want that current going anywhere else. You don't want that voltage staying hot on the module surface and then someone comes and touches it and electrocutes themselves. You don't want that voltage connecting to the rack and then connecting to the roof and then energizing the beams in the wall, and maybe the building is not connected to ground very well because it's on top of a concrete slab and it might not be that big of a building, so there might not be much surface area touching the slab, and then someone touches the wall of the building and electrocutes themselves. Now, you don't want any of that. You want a nice big thick piece of copper going up to the roof and touching your solar array, and that thick piece of copper coming down the sidewall and going straight into ground. Well, and your grounding system has to be continuous too. You can't have multiple ground references, because if you're just connected to ground here, then over here, if you're ground faulting over here, you might be raising the voltage in your ground and therefore making it impossible for the breakers to detect a ground fault. And so your grounding system needs to be continuous. And so here we have the electric ground conductor connecting all parts. And there may be a different size between this DC grounding electrode conductor and this AC grounding electrode conductor, because the DC is at a higher voltage and lower amperage, and the AC is at a lower voltage and higher amperage, and they can, you can combine the two, but you have to use the largest of the two. And if you combine the two, the bare copper comes from a number 6, comes from a special rule. And so if you deviate from that, you might find that you have to size this for every different project. It's just the easiest is to run bare copper up to the roof and land on the racking. Well, we're connecting to our inverter. And look, our inverter, when it inverts from positive to negative, our inverter is providing a neutral. And that neutral is being connected up to the neutral in our main service panel. And then that neutral is being run back to the utility. And so right here is that main bonding jumper. And so here we have a main bonding jumper occurring inside the panel itself. But that might be in the meter base rather than in the service panel. And so here we have a combo meter panel box with the main bonding jumper being made in the box itself. If you remove the meter panel from your main service panel, this bonding jumper point will likely travel with the meter up to the utility service disconnect at the meter itself. How do breakers work anyway? Well, it takes advantage of electromagnetic activity. What we have is this spring, and the more current that flows through this coil, we have an electromagnet here. The electromagnet, as current flows through, it attracts the switch and pulls the breaker up until it triggers a locking mechanism. Pop. You've blown your breaker. And so what happens is when you get an imbalance between a positive and negative, when you get a ground fault where current from one leg is faulting into ground, all of a sudden you have a mismatch in current between the other leg And so what's the definition of listed? If equipment, materials, or services on a list that's published by an organization acceptable to the authority having jurisdiction, that states that it's identified or tested for a specific purpose. And so you might find the greatest splice kit in the world that's made for, underground cabling, and you want to go use it up on the rooftop for your solar array. If it's not listed for use on a roof for solar electric wiring, you may fail your inspection. They have to be listed, and not just listed, but listed for purpose. There's certain restrictions. For flexible metal conduit for service entrances, it can't be over 6 feet long. Between raceways and other service equipment, cable trays can be used to support service entrance conductors, but only certain types. Different locations on where you can splice conductors. So where required, a box or conduit body should be installed at each conductor splice point where the wiring method is conduit tubing, AC cable, MC cable, MI cable, non-metallic sheath cable, or other cables. So typically you're doing splices inside boxes or conduit bodies or fittings. Now it's kind of interesting that you can do splices inside of conduit bodies, except where otherwise permitted. So in covered, accessible wiring methods such as auxiliary gutters, you can do splices. The splices are integrated directly into the equipment. If you have a type MI cable, that's a mineral sheathed cable, that's a little bit stronger than others. The definition of a fitting, an accessory such as a lock nut, a bushing, or other parts of a wiring system intended to perform a mechanical rather than an electrical function. And so the Loctite grounding screw, or it's called a lock nut, where your pipe goes into a box, and then you have a bushing that goes, a plastic bushing that goes over the edge to smooth out the end of the conduit. Well, you might need a lock nut, a fitting that screws in and tightens the conduit down onto the box. Well, every metal part needs to be grounded, and so does your fittings. And so, you have to, you might have a fitting that goes onto a metal box that needs to be grounded, or you might have a plastic PVC box, and if you're running metal conduit into it, you might actually have a lug on one of your fittings where you're grounding your bushing or your fitting onto the metal part of those fittings rather than onto the box itself, which is plastic. You might run from the fittings to a ground bar and from the ground bar to the other side of the fittings. Section 230.50, protection against physical damage. So underground service entrance requirements have minimum cover, wet location, raceway protection. If you're doing a direct burial, you need to put down a warning ribbon so that when you dig it up, you're able to stop digging right before you hit the buried power lines. All others shall be protected by rigid metal, intermediate metal, Schedule 80, EMT, reinforced conduit, something that's a little bit more robust. Other than service entrance cables, individual open conductors shall not be within 10 feet of grade level or exposed to physical damage, with the exceptions being more robust sheath wire. Mounting support, service entrance conductors, within every 12 inches of that gooseneck, within 12 inches of the raceway connection or enclosure, and then at intervals not to exceed 30 inches. And then for other cables that are not approved for mounting in contact with a building or structure shall be mounted on insulated supports at intervals not exceeding 15 feet in a manner that maintains 2 inches clearance over the surfaces that they pass. So we can see the solar conductors being held up off the rooftop through some conduit supports. And then we see those cables being supported at 12 inches through the masthead. So individual conductors entering buildings or other structures shall enter through bushings or through the wall in an upward slant through individual non-combustible insulating tubes. Drip loops shall be formed on conductors before they enter the building. So again, the utility has come on and tapped the your utility feeder conductors to their utility service entrance conductors, tapped them on here, formed a drip loop so water drips off instead of getting up into that masthead. Raceways to drain. Where exposed to the weather, raceways enclosing service entrance conductors shall be suitable for use in wet locations and be arranged to drain. When embedded in masonry, raceways shall be arranged to drain. So don't have it so that, if you're burying conduit in concrete, don't have it so that the conduit is on such an angle so that it will fill up with water if water gets into it. Service entrance conductors. Overhead service locations, the service head, the service entrance cables equipped with the service head or gooseneck, service heads and goosenecks with above service drop or overhead service attachment. Where impractical to locate the service head or gooseneck, locate within 24 inches of the point of attachment. All right. Services. Service equipment enclosed or guarded. Energized parts shall be enclosed or guarded. Enclosed means not exposed to accidental contact. Guarded means non-closed on a switchboard, panel board, and guarded. A means for locking or sealing doors providing access to energized parts shall be provided. So energized parts need to be enclosed and guarded. I remember one day on job site where the utility had come to wire up a new service, and we had run our conductors up, but we're still working on the inverter room. The utility came out to hang the transformer, and they went ahead and hung their wires as well, but they did not perform the tap. They just taped their utility service entrance conductors up and left them hanging. Later in the day, those wires hanging off of the utility transformer live, hot, touched the side of the building, and boom, it shocked the building and actually vaporized some MC4 connectors up on the rooftop. They were connected to the building ground. We just had high voltage electricity go through the side of the building. Well, that was not how it was supposed to be. The conductors are supposed to be, insulated. They were not enclosed. They were not guarded. Service equipment disconnecting means it needs to be in a readily accessible location, either outside the building or inside the nearest point of entrance of the service conductors. So, that solar service disconnect, what the inspector wants is it to be outside the building, so that the people who need to use it when they need to use it, which are the firemen, can quickly find it and de-energize the system. Maximum number of disconnects, I bet you can guess it already. It's 6. The service disconnecting means for each service shall not contain more than 6 switches or sets of breakers. There shall not be any more than 6 sets of disconnect per service group in any one location. So we're getting into that 6-handle rule. We're seeing it pop up not in just one place in code, but throughout multiple locations of code. So here we have a one-line diagram, and we have, multiple 200 amp breakers coming in, and then one main breaker. Now, this one main breaker was really not necessary. We didn't need to purchase it because we had a visible lockable disconnect with a fuse. Kind of fused a fuse. That was unnecessary. But what does this gain us? By having this main disconnect switch here, we can turn the fuse off and turn this switch off. And I don't know. It doesn't gain us very much, does it? If we had tied in more than 6 of these 200 amp breakers, then we would have had to have a main on here so that you could turn off one breaker and kill power to the utility. And then here's our one-line diagram of solar edge micro invert optimizers going into each solar edge inverter. And on these service panels here, we have 1, 2, 3, 4, 5, 6 inverters. So actually on this distribution panel, we don't need to have a main breaker. It could just be a main lug only without a main breaker, since we only have 6 of them on each panel. If we had 7 on each panel, then we would need to have a main breaker. So this might be a distribution panel without a main. Here's a distribution panel with a main. I'm sure that surprised all of you. Maximum number of disconnects. Disconnecting parts of listed equipment shall not be considered the service disconnect for power monitoring equipment, surge protection devices, control of a ground fault protection system, or power operable service disconnecting means. So if you want to put an additional disconnecting means onto the system that's power operable, you can. It might not be hand controlled. It might be above and beyond what you need. You still need a hand operated switch out there. That power operated switch would not be counted. Still could be by your local jurisdiction though. Let's see. Additional service disconnection means. One or more additional service disconnecting means for special cases permitted by that section we saw before, like solar equipment, shall be installed remote from one service disconnecting means for normal service to minimize the possibility of simultaneous interruption of supply. Which means that if we have special switches for standby systems or for emergency backup systems, those switches need to be grouped in a different location so that in the frenetic moment of closing all these switches, you don't close the wrong switch and turn off the backup power supply without intending to. Although the best way to do that would then to have a placard that says backup power this way, and maybe within 10 feet of the service disconnecting switches, you have your backup disconnect and emergency disconnect in a very clearly labeled manner. I don't know, maybe you put the backup disconnect switch on the other side of the wall. So it just depends. 230.72, the grouping of disconnects. Additional service disconnect means the one or more additional service disconnecting means for special cases permitted by 32, generators, energy management systems, which would include batteries, solar arrays, windmills, energy generation devices, shall be installed remote from the one service disconnecting means for normal service to minimize the possibility of simultaneous interruption of supply. So does that mean our solar disconnect cannot go right next to our main service panel? Perhaps, but is your solar array being used as a piece of standby equipment or not? disconnects. If you have a standby power system that's supposed to kick on when the power goes out, those disconnects need to be in a different location than your main service disconnect. And you should have a directory which directs the firemen to that location in case they need to be turned off. Equipment connected to the supply side of the service disconnect. So only the following equipment shall be permitted to be connected to the supply side of the service: current limiting devices, meters and meter sockets, meter disconnect switches, surge arresters, surge protected devices. Equipment connected to the supply side of the service disconnect. Taps to supply load management devices, fire alarms, standby systems. You might wire the fire alarm up to the supply side so that it still works even if the power is turned out to the property. If they lock out your electric service panel. And short circuit current rating. The current at nominal voltage to which an apparatus or system is able to be connected without sustaining damage exceeding the defined acceptance criteria. So, what's the current that if the system exceeds it, it sustains damage? It's not the nominal current, it's the short circuit current. Overcurrent is any current in excess of the rated equipment or ampacity of the conductor. What can cause an overcurrent situation? Well, if you plug in too heavy a load, maybe you put 30 amps of devices on a 20 amp circuit, or if you're short circuiting. If that power supply is draining directly into the ground, it's a ground fault or short circuit, causes overcurrent, even if just for a split second until the breaker switches over. And so we have an overcurrent protection device, which is a device providing protection on the service feeder or branch circuit, which we know now is a breaker or a fuse, over the full range of overcurrents between its rated current and its interrupt rating. So these can be breakers or fuses, as we see in the picture. Where is service equipment overprotection required? It's not required to be higher than the ungrounded conductor's allowable ampacity. And so if you have 40 amp cable, your overcurrent protection cannot be a 50 amp breaker. If it's a 50 amp breaker, then you could pull 50 amps through it. It's rated for 40 amps. It could heat up and catch a fire. Not in the grounded conductor. So you don't put overcurrent protection. You don't put a fuse in the neutral wire, except a circuit breaker that simultaneously opens all conductors of the circuit. And so if you don't have you might have a separately derived system that produces its own neutral, such as a generator, at which point you don't want to reference the neutral from the power line anymore. And so your transfer switch may just open and have to be physically reset because the generator is providing its own neutral. You don't have a neutral that's bonded in to the entire system. That's okay, that's allowable, but if that's the case, you need that breaker to simultaneously open all the conductors, not just the neutral wire, but also the positive and negative as well. Section 240, overcurrent protection. Current limiting overprotection devices. Protection of conductors for overcurrent devices rated at 800 amps or less. We're allowed to do the next higher standard overcurrent rating above the ampacity of the conductor being protected is allowed to be used under certain conditions. The service equipment overcurrent protection should not be higher than the ungrounded conductor's allowable ampacity. And so the main service breaker is not sized to be larger than what the conductors can handle. But then when you get into smaller cable, we have protection of conductor overcurrent devices rated at 800 amps or less, where you actually are allowed to use the next highest level up above the ampacity of the conductor being protected. And so as soon as that conductor begins to draw more current than what it is sized for, it'll heat up. If it draws too much current, it'll flip the breaker. So what are our standard breaker sizes? We got a 15 amp, a 20 amp, then we go 25, all the way up to 50. 60, 70, 90, 80, 90, 100, 110. So, it goes up by 5 amps up to 50 amps. Then it increases by 10 amps each. Increases by 25 amps each. Then as you get into larger and larger sizes, 50 amps, 100 amps. And so the larger in power you get, the less selection you have in breaker size. And so the smaller amperage, the smaller breaker ratings, you actually have a lot more selection, a lot more granularity. So they let you size up to the nearest one. Once you start sizing conductors in the 800 and 1000 and 1200 amp range, you're getting into commercial or utility scale projects, at which point you're not rounding up to the nearest breaker size. You're sizing the conductors to handle the entire current. And if the current in those conductors that are sized for the entire current elevates to beyond that, it trips before you start smoldering wires. Because there's a lot of power difference between, say 1600 amps and 2000 amps. So, can you use additional overcurrent protection? Additional overcurrent protection, such as the breakers in your combiner box, are not a substitute for branch circuit overprotection. But on the other hand, if you are using supplementary overcurrent protection, it does not need to be readily accessible. So the breakers on your service panel, those need to be readily accessible. The main breakers that the branch circuits are plugged into. But if you have an additional fuse or additional breaker, say up on the rooftop where you're combining circuits together, that is not a substitute, but it also doesn't have the same accessibility requirements. Ungrounded conductors, well, that's what we need to protect against. Those are the leg 1 and leg 2 high voltage power branches. And they need to be on circuit breakers that can be operated manually. So where can we put these? Well, in the battery conductors, they have different rules than the others. In battery conductors, overcurrent protection shall be permitted to be installed as close as practicable to the storage battery terminals in an unclassified location. So installation of overcurrent protection within a hazardous location shall also be permitted. So where do our branch circuits receive their supply? At the main service panel. But there are some exceptions. Branch circuit conductors. Feeder taps under certain conditions. If they're properly sized, enclosed, and not over 10 feet long, and not extending beyond the devices they supply, then it doesn't need to be protected. Line side tap, that's within 10 feet of your main, that may always be hot. If you have a main lug only box, it may always be hot going into the top of that box. The grounded conductor. No overcurrent device shall be connected in series with any conductor that is intentionally grounded, such as a neutral line, unless the overcurrent device opens all conductors of the circuit, including the grounded conductor, and is designed so that no pole can operate independently. And so what that might be is the connection at the utility service, where if you cause a power surge between the service conductors and your main home, you may actually trip a fuse up in that transformer, and at which point it would disconnect all the poles to your house, and the utility's going to have to come back out and see exactly what you did before they reestablish power. A similar thing can happen with your main service panel and your main breaker. The only exception would be on a motor circuit. You may put a overcurrent protection device into that grounded neutral, or you might have a grounded negative to provide some additional protection of your motor. Now, change in size of the grounded conductors. Whenever a change in size occurs of the ungrounded conductor, a similar change in size shall be permitted to be made in the size of the grounded conductor, which means that if you're upsizing your cable due to voltage drop, you also upsize your neutral. If you have an undersized neutral, you still give it +1 size, similarly to the upsizing of your conductors. Location in or on premises, the accessibility. Switches containing fuses and circuit breakers shall be readily accessible. So, we have that combiner box on the rooftop, and your inspector may say, well, that needs to be readily accessible. Accessibility. Switches containing fuses and circuit breakers shall be readily accessible, installed such that the center of the grip of the operating handle of the switch or circuit breaker is not more than 6 foot 7 feet above the floor or working platform, unless for busways, supplementary overcurrent protection, or being located adjacent to the utilization equipment they supply. Exception, the use of a tool shall be permitted to access overcurrent devices within listed industrial control panels or similar enclosures. What does this mean? Well, this means that for your code mandated switches and fuses, they all have to be accessible by someone who can just reach up and flick the switch. If it's an additional disconnect, like you might have an additional disconnect next to a piece of air conditioning, and they put an additional disconnect there so that you can just interrupt the conductors and service the air conditioning, that may not have the same accessibility requirements as your main disconnect switch. Protection from physical damage. Mounting on open type switchboards, panel boards, or control boards that are in rooms or enclosures free from dampness and easily ignitable material and are accessible only to qualified personnel. Operating handle. The handle of a circuit breaker shall be permitted to be accessible without opening a door or cover. Enclosures for overcurrent devices in damp or wet locations should comply with 312.2. We haven't gotten to that yet. And then, this is a 240.33, vertical position unless shown to be impracticable. And what that is talking about is that the switch needs to go up and down. So you have a knife switch disconnect, and here's your box, and here's the knife switch, and that needs to be in an up or down location rather than, putting it on its side and having the switch be kind of in a left or right location based on where you are, up and down. Now, what does that mean for a breaker switch? Our breaker switches on our loads are side to side, but then we have our main breaker switch that's supposed to be up and down. So that's what we're saying, is that wherever this switch occurs, if it's possible, that should be in an up and down location. So if you have a box with a single pole in it, but they still want you to put a breaker box there to be used as a system disconnect, as an external disconnect, that's just not a knife switch. A breaker box is cheaper, so you get a breaker box here, and then you have a switch that can kind of go up and down. You can't put that switch on its side if you can otherwise locate it so that it toggles up and down. So your switches go up and down. Grounding and bonding. What needs to be grounded and bonded? Systems, circuits, equipment. You might have certain circuit conductors. We get into the types and sizes of grounding and conductor requirements and methods of grounding and bonding. So for that, we need to revisit some definitions. We have the bonding jumper supply side, a conductor installed on the supply side of a service or within service equipment enclosures for a separately derived system that ensures the required electrical conductivity between the metal parts required to be electrically connected. So a bonding jumper will bond metal parts. The effective ground fault current path, an intentionally constructed low impedance path intended to carry current from the point of a ground fault to the electrical supply source, which triggers the overcurrent protective device or the ground fault detector. And that should be compared to not the effective ground fault current path, but a ground fault current path, which is more generic. It's an electrically conductive path from the point of the ground fault in the wiring system through non-current carrying conductors and equipment to earth to the electrical supply source. So, anything that is metal, through your equipment ground conductor or your metal housing that's connected to that is a ground fault current path. Then we have an effective ground fault current path, an intentionally construed low impedance path intended to carry current from the point of a ground fault to the electrical supply source and trigger the overcurrent protective device or ground fault detector. I'm thinking about that time when utility service entrance conductors touched the side of a metal building and it blew up some MC4 connectors on my building, just pulverized them. And I was thinking to myself, well, what does that mean? How did the electricity get from the side of the building into the cables of the solar array enough to cause an arc fault to blow the cables apart? I was thinking, well, the module frames are connected to the racking, and the racking is a ground path, and the racking has a ground path that go into the building girders, which are attached to the building, and none of those are considered to be an effective ground path. We have a piece of copper wire going up to the rack, then hanging over the side of the building and going into ground. So maybe it was that the building wall, the metal building wall, did not have an effective ground path to ground. Maybe their bolts were, or maybe the bolts that went into the concrete were considered to be the ground path, but they were never tested, and concrete does not have the resistance that you think it does. So maybe the side of that metal building actually was not grounded. And so there was a new ground path. The ground path went up into my solar array and up into the module frames and made its way into the current. So the effective ground path is the intended ground path, whereas a ground fault path could be, any ground fault path. And you'll see that referenced. Electrical system grounding. Grounded systems will limit the voltage imposed by lightning, line surges, or unintentional contact with higher voltage lines and stabilize the voltage to earth during normal operation. Normally non-current carrying conductive materials enclosing electrical conductors shall be connected to earth to limit the voltage to ground on these parts. Alright, so all of our metal parts are connected to ground to be at 0 voltage, so that we don't walk up to them, touch them, and electrocute ourselves. The bonding of electrical equipment shall be connected together and to the electrical supply source in a manner that establishes an effective ground fault current path. So here we have a mandate that says you can't just touch a whole bunch of metal together and say that it's continuous. You have to have an effective ground fault path where all the pieces of metal are connected together and to the electrical supply source in a manner that establishes an effective ground fault path. So we cannot just have a billion different ground fault paths on our system. One for that section of building, another for another section of the building. All of your electrical system in that building must be bonded together and have a single effective fault path to ground. Connection of bonding and grounding equipment. So there's a wide number of ways that you can connect pieces of metal to the grounding system. You may put a terminal bar together. You can weld. You can use grounding screws, which are machine screw type fasteners, listed grounding assemblies, pressure connectors. Pretty much the only kind of attachment that can't make a ground path between two pieces of metal is either butting them up next to each other, just touching them, or solder. Here we have a grounding wire connecting to a piece of copper. Now it's a ground clamp. That's a ground clamp. One thing that kind of shook me is that ground clamps or other fittings exposed to physical damage shall be enclosed in metal, wood, or equivalent protective coverings. So where I'm used to seeing these ground clamps is on your lightning rod. People call it a lightning rod. It's really not a lightning rod. It's a ground rod. It's an 8-foot long or 10-foot long piece of copper that gets hammered into the ground next to your building. Sometimes you need heavy equipment to install them. You know, about 3/4 of an inch wide, you know, copper coating. And it, you know, what it's intended to do is get some resistivity between your grounding system and the earth. You know, just sitting on top of the earth may not ground your building. And there may be some impedance from the soil. So, you know, getting a copper pipe 8 feet long driven into the ground gets you a little bit more conductivity, a little bit less resistance. Well, so you'll run your bare number 6 down to the ground rod on the side of the building, and then you'll use, you know, the construction jargon for this is called an acorn. It kind of looks like an acorn, I guess. But to connect your ground up to it, well, then it has to be protected, because someone could come along and kick that thing, and all of a sudden you have an ungrounded system. You know, surface treatments should be looked at a little bit more by the installer. For one, the surfaces need to be clean, but not just clean. They need, you know, if you have a non-conductive coating, if your metal has paint on it, or what's common in the solar industries, your module frames will have a anodized coating on them to make them look nicer and also to give them some weather protection. But you need to scratch through that coating for a module to be connected. And so we have these grounding screws which will bite into the module frame to ensure that this module frame is actually connected to the rack below. And the rack will often be a listed assembly that's listed as a ground path. And so you simply connect your ground to the racking. The racking is listed as an assembly, as a ground path, and then use grounding washers to ground the metal module frames to the railing itself. But on top of that, you'll find brand new components being manufactured, and maybe to keep the threads nice, they put a little enamel coating on them, or coming off of the manufacturing process for whatever reason. I used to run in, I've heard this is an issue sometimes with some brand new SMA inverters that come pre-wired up. Maybe the pre-wiring, the installer didn't note that there was a little enamel that needed to be rubbed off the end of the wires. That would be causing you know, a circuit not to energize, or an arc fault or something like that at the point of connection. Now, alternating systems should be grounded. DC systems do not need to be grounded. They shall be permitted to be grounded. And what that means is now we start to have DC systems where the inverter does not need a reference to ground in order to detect a ground fault. And so you have what's called an ungrounded inverter. It doesn't mean that it can't detect ground faults, but what it means is the DC side of the system is completely isolated from the AC side of the system. And that's actually safer, because that means if you do have a ground fault in the DC side, it doesn't impact the ground fault detection of the AC side, which was related to the blind spot in kind of old style commercial inverters that were grounded inverters. The grounding electroconductor from the connection shall be made at any accessible point from the load end of the service drop to the terminal to which the neutral is connected at the service disconnect. And so we have our main service panel, the load of the main service panel. You might draw your grounding electroconductor off of and drop into the ground, or that grounding electrode could be made all the way up to your utility service disconnect, where you're also bonding the neutral to your ground. So your ground rod could be out at your utility service disconnect. Your ground rod could also be at your load center, or it could be anywhere in between. So if you need to run your cables outside, you know, go do it. Now, load side grounding connections, the neutral on the load side, and this is what you have to be careful of. A neutral on the load side shall not be connected to the equipment grounding conductor or be reconnected to ground on the load side of the service disconnecting means except as otherwise permitted. What that means is if you have a lot of experience in the utility sector, you may be hanging your own transformers and then establishing a connection to ground on your new electric service. Then you get out to an existing electric service and you will not be providing that neutral bond to ground because it's already made if you're coming into an existing neutral service. So you just have to be on the lookout for that. The main bonding jumper is an unspliced connection between the equipment grounding conductor and the neutral within the service disconnect. So it can't be spliced. For grounded AC systems under 1,000 volts, the neutrals shall be rounded with ungrounded conductors to each disconnecting means. A bonding jumper shall connect the grounded conductors to each service disconnecting means enclosure.